Hello everyone. I welcome you to the live section of the course Introduction to Laser. I'm Gitanjali Jaina. I'm a PhD student from IIT Delhi. I'm also a TA for this course where I will teach you about the concept and I will revise the concept as well as I will go through the doubts that you must be having for the assignment or any conceptual doubts. And I will solve some additional problems in the meantime also. We'll look into the concept as well as the problems and your doubts. So in the last section, we have seen about what are the ray transfer metrics and what is the stability condition and what is the stability diagram. So before starting this section, let me ask whether you have any doubts in the current in the assignment 6 because the solutions has been released, I think. So whether you have any doubts in the solution of assignment 6. So if you have any doubts, please feel free to ask me or so let me unmute you all and you can speak, you can tell your doubt directly or you can write it down in the chat box also. So let us go through your doubts first, then we'll start the section. So in assignment 6, do you have any doubts in any one of the question? Or do you want me to show the steps for the solution of assignment 6? Anything? Uh, any doubts or any problem in the steps or whether you are not getting the answer which has been released in the forum? You can write it down in the chat box as well as you can speak also. Okay. So it seems you have no doubts for the assignment 6. So okay, so then let us move to the concept and the lecture. But if you have any doubt in any of these problems, then please free to ask me or you can write it down in the chat box. Okay. So let us see what where we have left. So we've seen about what are the stability condition, what are the ray transfer matrix for different types of resonator. And we are left with one final slide, which is the ray paths in spherical mirror resonator. Okay, so these are some recalls. That is, what are the relation between the position and angle that the ray makes after any type of after any time in the during the. um, Please provide transcripts and lecture slides for better answering assignment questions. Lecture slides, I think it's already available in the portal, I think, if I'm not wrong. Transcripts also, they usually provide the transcripts also. These are all, I think, these are all handled by NPTEL team. Only 4 weeks available. Okay. So then week 6 and week 5, For these 2 weeks, no lecture slides and transcripts are available. If you want for week 6, it's already in my Google Drive link. I have already uploaded week 6 lecture slide in that folder. I think you all have access to my Google Drive link, right? The link that I have created for this course. There you can see the week 6 link, week 6 lecture slides. And I will, if week 5 is not available, then I will upload the week 5 slides in the Google Drive link. Okay. So these are not issue. Transcripts, these are, I will tell the NPTEL team to provide the transcripts for week 5 and week 6. If so, transcripts and lectures. So is it clear? I will upload the week 5 slides. Week 6 slide is already there in my Google Drive link. You can visit that folder and get the lecture slides. So is it okay? Or any other thing? Okay. And so let me ask again whether you have any doubt, because some joined later in this live section. So whether do you have any doubt in the week 6 assignment? The solutions has been released. So if you have any doubts in the solution, then you can ask me. Otherwise, we'll move on to the concept. Okay, so let us see what is there in the remaining part. So, so inside is spherical mirror resonator. So we have this ray transfer matrix relation, which is Ym plus 1, theta m plus 1 is related by the ray transfer matrix, which is ABCD Ym theta m. So Ym defines the position with respect to the optical axis, position of the beam with respect to this optical axis, and theta m is the angle made by this ray with respect to the horizontal. So these are all related by this ray transfer matrix, which is ABCD. So the values for ABCD, these are all you got from the by multiplying the ray transfer matrix for propagation, a ray transfer matrix for reflection. So after doing all that, you got the value of A as 1 plus 2L by R2, B is this, C is this, and D is this. So you don't have to remember all this because these are all other than A, these are all long equation. Don't have to remember all this equation. So you just have to remember what you did to derive this to get this final form. So please just remember the steps. Then you can get the what is the value of A, B, C, D in the problems. Okay. And then we have seen about what are the resonator stability diagram. So these resonator stability diagram, it's a diagram between, it's a graph, it's a plot between G1 and G2. So what are G1 and G2? G1 is 1 plus L by R1 and G2 is 1 plus L by R2. So L is the separation between this mirror resonator, and R1 and R2 are the radius of curvature of the mirror. Okay. So from that you get this type of plot, one in the first quadrant and one is the third quadrant. So the shaded region is the region where we see the stability of this any type of mirror resonator. So let us see. So we have seen three cases. One is where both these mirror are plane mirror resonator. So when we have plane mirror resonator, both R1 and R2 are infinity. So for that case, both G1 and G2 values are 1. So this means this G1 and G2. So the stability condition that we got in the final is 0 greater than less than equal to G1, G2 is less than equal to 1. So if you see the plane mirror, both G1 and G2 is 1. That means it satisfies this stability condition. So that means we can take two plane mirror resonator to get a mirror resonator for a laser. And second case that we have seen is the symmetric confocal mirror resonator. So when we talk about confocal, that means the L. So what will be L? L would be 2F. So it will be, if you want to write it in terms of radius of curvature, so it will be 4F. Sorry, 4R, not F, 4R. And depending on the, so we have seen if you take two symmetric concave mirror, then for concave mirror, R is negative, right? So that means, so F is R by 2, right? So there is a mistake here. So F is R by 2. So this means this will be R. For concentric, it will be different. For concentric, it will be different, but when it is confocal, so L would be 2F or it is equal to R. And for concave, it is R is negative. So this means L is minus of R. Okay. For this case, we get G1 and G2 as 0. So this means this also satisfies the stability condition. And if you want to point this location of this symmetric mirror resonator on the stability diagram, so that means the origin of this stability diagram defines the confocal symmetric mirror resonator situation. So this point will be it will define the resonator for confocal mirror resonator. And the third case is concentric mirror resonator. So in this case, L is minus of 2R. So for this case, G1 and G2 is negative, which so if you take the multiplication of G1, G2, it is 1. So it lies between 0 and 1. So that means for all these three cases, we see this defines the stability. This satisfies the stability condition. And for all these cases, they lie in a straight line. So for symmetric, it lies in this straight line. So origin is confocal, 1, 1 is plane mirror, and minus 1 is the concentric mirror resonator. So let us see one by one cases. So first one is plane mirror resonator. So we have seen this satisfy the stability condition, that is. So please remember all these important conditions. So this won't be given in the uh, question paper. So you have to remember all these conditions. So for stability condition, this should satisfy 0. G1, G2 should lie between 0 and 1. And we have seen for plane mirror resonator, this G1 is 1 and G2 is 1 because R1 and R2 they are all infinity. Also, G1, G2 will be equal to 1. Now we've seen what are the solution to this solution of position of the ray in this mirror resonator. So we have seen it is harmonic. And we have seen in the earlier lecture by taking a trial solution, we have seen we can write the position of the ray using this form. So Ym is equal to Ymax. Ymax is the maximum position that the ray can go from the optical axis. So Ym is Ymax sine m5 plus phi 0. So to see after how many round trips the ray will retrace the path. So for this case, let us see what are the boundary conditions. So the boundary condition is when m equal to 0, what will be the ym, and what is the relation of ym with y max? So sin phi 0, if you put m equal to 0 in this equation, so we'll get sin phi 0 as y0 by y max. So you have to remember all these steps, how you got the value of B, and after how many round trips you will the ray will retrace the path. So you have to remember all these steps. So if you remember all these steps, then the remaining will be easier for you to calculate. So first we'll see what is the condition for m equal to 0. So this will indicate that phi 0 will be sin inverse y0 by y max. And the matrix elements you can easily find out. So please recall these are the relation between A with the radius of curvature and the length of the resonator. So as I said, you don't have to remember all this. You just have to multiply all the metrics related to reflection and propagation and get these values. So these are all the relation A, B, C, D. So if you put the value of L and R as infinity, so we will get A equal to 1, B equal to 2L, C equal to 0, and D equal to 1. So that means the main, so one stability condition is 0 less than equal to C1, G2, which is less than equal to 1. And another type of stability condition we have seen is -1 less than equal to B less than equal to 1. So in terms of G1, G2, this is the stability condition. In terms of B, this is the stability condition. So you have to remember these two stability condition. These are preliminary. So if you remember this, then everything will be easier. So we have calculated what are the values of A, B, C, D. And B is related to A and D only. So B, we have seen it is A plus D by 2. So from this, you will easily see B equal to 1. And if you recall, I is nothing but cos inverse B. So that means we have seen the V value is 1. So this is cos inverse of 1. So that means you can write it phi is 2 m prime pi. So if the theta, it is even multiple of pi, then you will get a value of 1 for the cos function. So the phi value that we got is 2 m prime pi. So now you just have to put the value of pi in the expression, this ym equal to y max sin m pi plus phi 0. And this is the final form. And if you see, this is nothing but some multiple of pi, right? Some multiple of pi. That means if you sin pi plus phi, it will be sin phi 0, right? Some even multiple of pi. So that means you will get the ultimate equation is ym equal to y max sin phi 0. So that means this ym, that is the position of the ray after round m uh, round trip, then it will be y max sin phi 0. So ym is independent of the number of round trips. So there is no dependence on phi. So that means you will, so if you want to find out what is the value of phi 0, that is the initial angle that the ray makes with the axis, that is this angle. So you have initially started from this position. This is y0 and this is phi 0. If you want to find out what is the value of phi 0, then phi 0 will be sin inverse ym by y max. And for m equal to 0, we have y0 equal to y max sin phi 0, which is nothing equal to ym. So this indicates ym for any value of m, this is equal to y0 only. So we initially started with y0 then after for any value of m, we see that the position remain unchanged. So means the height will be same for all round trips. And if you want to find out what is theta m, so theta m, this is the equation for theta m. So theta m is nothing but ym plus 1 minus aym divided by b. And as we have seen, for any values of any values of m, ym is always y0. So that means this theta m, it is 0 because ym plus 1 is y0 and a is the value of a is 1 and ym is also y0. So that means this theta m, it is always 0. So theta m plus 1 will be always 0. So that means the ray makes 0 angle with the optical axis, with the horizontal axis. So the allowed ray path in a plane mirror resonator is the path where the theta m is 0 and the ym, it remains constant, which is y0. So that means the ray travels like, so the ray, it is perpendicular to the mirror surface, so that the theta m is 0 and the ym remains unchanged during this uh, oscillation inside this plane mirror resonator. Other than this ray pass, if the ray makes any small angle, that is this ray, so what will happen? This will eventually escape out after few oscillations. So that is why this is not the allowed ray path in a plane mirror resonator. So this ray path which makes angle with the resonator, so they will, after some oscillation, they will eventually escape out from this setup, plane mirror resonator setup. So the plane mirror resonator, please remember only the ray path that is parallel to the axis. It is that is only confined and others are not confined inside this plane mirror resonator. Okay. Uh, so, uh, so what you have to remember? So you have to remember what is the, we have to remember this relation, that is ym is y max sine m phi plus phi 0. And you have to remember how you can calculate. So for this, you have to calculate what is the value of phi. So phi, how you can calculate? So phi, you calculated from b value. And for V value, we derive the value of B from the ray matrix, that is ABCD matrix, where B is A plus D by 2. So only this much is enough to solve any problem. Okay. And next is the symmetric confocal mirror resonator. So we have seen in the plane mirror only the ray path that is parallel to the mirror axis is confined. So in a confocal mirror resonator, we have already seen the ray paths in few, I think, last week live section. So now we will numerically derive what is the ray paths. So for confocal, we have, so we have this, so if you see this two setup, so these are two mirror, concave mirror of radius curvature R and R. And for this setup, it's a confocal setup, that means the common point, that is center point, is the focal point. So that means L, it is 2 times of F, and F is R by 2, so this is R. And for concave, it is minus R. So that means we see this is L equal to minus R. And for the matrix, so first we have to calculate what is the value of B, that is the value of A and D. So A value we can easily get, it is minus 1. So please use this relation to find out what is the value of A, B, C, D. So the value of A we got is minus 1. The B value is 0. C value is also 0 and D value is minus 1. So that means A and D both are -1. And so B value is -2 divided by 2. So it is -1. Okay. And we got the value of B. Now we can easily calculate what is the value of phi. So phi is nothing but cos inverse B, which is it is B is -1. So that means the phi, it's an odd multiple of pi. So for n equal to 0, 1, 2, 3, we have phi is -1. So sorry, cos phi is -1. So now we got, so from B, we got what is the value of phi. Now we'll see the ray paths. So Ym, so ray paths are calculated using this relation. Ym is Y max sine M phi, this is the phi value we got, plus some initial phase, phi is 0. So from this relation, we got is, so the odd multiple of pi, so this may be -1 to power m. So depending on the value of m, it can be -1 or it can be +1. So we got this relation. This is -1 to power n y max sine phi 0. And what is this relation? This is nothing but y0, right? So that means we got the relation of ym with y0 is ym is -1 to power m y0. Now, if you start with m equal to 0, for m equal to 0, we are taking the ray paths in the initial situation. So that means for m equal to 0, y0 is y0. And for m equal to 1, so we have y1 is minus of y0. And when m equal to 2, it is y0. For m equal to 3, it is negative y0. So that means if you see in the diagram, so we have started from this, let's say we have started from this point, right? It is y0. So when this ray, let's say this parallel ray, which is moving parallel to this setup. So as this is parallel to this setup, so it will, after reflection, it will go through this focal point, right? So it will go through the focal point, and this is y1. After coming here, it will be y1. And you can see from here, y1 is nothing but negative of y is 0, right? And whenever after reflection, this ray will become parallel to the setup. And this will be reflected to this initial position. So here we can see after so the ray will move like this parallel to the surface. It will be reflected back to the first mirror again with a value of y1 is minus of y0. And after this, it will again reflected back to this second mirror and again reflected back to the first mirror. So this is one type of ray path. And the second type of ray path that we have is when the ray is passing through the center of curvature. So when the ray passes through the center of curvature, it will be reflected back again. Okay, so these are the two types of ray path in a symmetric confocal mirror resonator. And here we can see the ray path is alternatively it is becoming minus y0 for the odd value of m, and for even values of m it is plus y0. Okay. Now we'll see what is a symmetric for symmetric concentric mirror resonator. So for confocal we have L equal to minus R, and for concentric we have L equal to minus of 2R, because the center point is, it is not R. So it is not F. The center point is defines the radius of curvature of each mirror. So that means this distance is R and this distance is also R. And so this means L equal to minus of 2R for concave mirror. Okay. So we got the value of L. What is the relation between L and R? Now we can easily find out what are the values of A, B, C, and D. So that means the value of B will get is, what is the value of B? B is A plus D by 2, which is minus 3 plus 5 by 2. So we'll get value of 1. So it satisfies the stability condition. Now from B we'll calculate what is the value of 5, which is nothing but cos inverse of B, which is 1. Now it is the cos phi is 1, so that means it's a even multiple of pi. So now we have to use the ray equation, which is ym equal to y max sin m phi plus phi 0. So it's a even multiple of phi. This means this relation you can write it as y max sin phi 0. I think you can, I'm assuming that you can get this equation from this. So use this the formula sin a plus b formula. Sin a plus b is sin a cos b plus cos a sin b. From this relation, you can easily find out what this relation y max sin phi 0. And this y max sin phi 0 is nothing but y0, right? This is y0. So that means this value ym is equal to y0. This is the relation we got. And what is the value of theta then? So theta we can calculate from here by putting the value of ym plus 1. So ym is equal to y0. That means this value, it is y0, and this value is also y0. And the value of A here is not 1. So for plane mirror resonator, we have seen A equal to 1, but here it is minus 3 for concentric mirror resonator. So the theta m value we'll get is ym by r, which is y theta by r. So this theta m is independent of m. So this theta remains constant as the ray oscillate inside this mirror resonator. So now let us see the ray diagram. So if you see inside a concentric mirror resonator, so we have seen the allowed ray path is where ym is y0, ym is y0, and theta m is y0 by r. So if you have started from, let's say, from here, where it satisfy both this condition, ym and theta m. So what we'll see? We'll see this ray will travel through this center of curvature, and during oscillation, it will be reflected back in the same path because it passes through the center of curvature. Okay. So that means after one reflection, it will be y0 only. And also this path and this path. Any ray path which passes through the center of curvature and satisfy this condition. Ym equal to y0 and theta m is y0 by r. So in the plane mirror, we have seen this initial condition, but for plane mirror, theta m is 0. But in concentric mirror resonator, theta m is not 0. Theta m is y0 by r. So I hope this all these steps are clear to you. So first we have to calculate what are the ray transfer matrix, what are the value of. So let me write down the steps. So first we have to find out what are the ray transfer matrix, RTM. Then from using RTM, you have to find out what are the values of what are the value of B. From B, you have to calculate what is the value of phi. And using phi, you have to put in the ray equation, which is ym equal to y max sin m phi plus phi 0. And using this, you can easily find out what is the, just put the value of phi and initial condition to get what are the array paths for array condition for ym and theta m for a given type of resonator. So these are some special cases like plane mirror resonator, confocal and concentric mirror resonator. So now we'll see a general case where we have a spherical mirror resonator with a value b equal to 0.5. So first check whether it is satisfies the stability condition or not. So stability condition is for b, it should lie between -1 to 1. So as it is 0.5, so this means the stability condition is easily satisfied. Now from b, we have to calculate what is the value of phi. So phi is cos inverse b, which is nothing but pi by 3 plus some even multiple of pi. Okay. So you already know cos pi by 3 is half, right? Is 0.5. So if you take some pi by 3 with some even multiple of pi, so we'll get back half periodically. So that is why we have taken pi by 3 plus 2p pi, where p is 1, 2, 3. Okay. Now we just have to put these values of pi in the ray equation. So as I said, we have to put it in the ray equation ym equal to y max sine m pi by 3 plus 2p pi plus phi 0. Now you see there is a 2 pi term here. If you open up this bracket, there is a 2p pi term here. So that means this ray equation you can write it as y max sine m pi by 3 plus phi 0. Right? So sine 2 pi plus some constant. Let's say phi 1. It is nothing but it is equal to sine phi 1. So that is why we have taken out this 2p pi term. Now, as I said, we have to see what is the initial condition, that is for m equal to 0, the y0 is y max sine phi 0. Now, if you want to find out what after how many round trips the ray will retrace the path. So for this case, we have to see for which value of ym this ym is equal to y0. So that means the position become equal after this m number of round trips. So that is why we have equate this equation y0 equal to y max, and y0 you know it is nothing but y max sine m pi by 3 plus phi 0, and y0 is y max sine phi 0. So y0 max, y max, they will cancel out. So the equation that remains is sine m pi by 3 plus phi 0 equal to sine phi 0. So that this indicates that the term here, that is this term, this must be a integral multiple of 2 pi. So this means this m pi by 3, it is integral multiple of, let's say, 2p pi. So that means the m is nothing but 6p. And for if you want to find out what is the minimum number of round trips, so for that we have to take p equal to 1. So that means m equal to 6. So this indicates that the ray will retrace the path after 6 number of round trips. Okay. So these are the steps to follow to find out what are the minimum number of round trips to follow, so that the ray will retrace the path in each oscillation. Okay. So the steps, as I said before, first we have to calculate what is the value of b. From b, you have to calculate what is the phi, and from that we have to calculate what is ym, and by equating ym with y0, you can find out after how many round trips the ray will retrace the path. So these are the general steps. So, so till now, do you have any doubt in any part? Okay, so let us see some of the ray diagram inside a mirror resonator. So up to now, we have seen what is the value of Ym time for the ray to confined inside the resonator. Now let us see what are the visual representation of this ray paths. So we'll see the ray paths in a spherical mirror resonator. So this is the case for a mirror. So R1 is minus 80 cm, 80 centimeter, and R2 is minus 80 centimeter. So these are two symmetric concave mirrors, which are separated by a distance L equal to 70 centimeter. Using this equation, you can easily find out what is the value of G1 and G2. So the G1 and G2 we got is these values, which is 0.125 and 0.125. So this easily satisfies the stability condition. So that means the ray will be confined inside this resonator. So these are some ray paths. You can see the ray, it is traveling from one mirror to other mirror, and it is constantly moving back and forth inside this mirror resonator, and it is confined inside this resonator. It is not escaping outside in from the mirror resonator. And for the same case, so we have another type of ray diagram where the rays are confined in this manner. So this may indicate a different value of theta m or ym for a given symmetric concave mirror resonator. Or if you go higher, then it may indicate the a different type of mode of this concave mirror. So here we can see the ray is confined inside this mirror resonator, and it is constantly moving back and forth from one mirror to other mirror. And this is the same for same symmetric concave mirror resonator. Another type of ray diagram where the value of ym and theta are different. So these are three different types of ray diagram for the same case. Here you can see the beam is narrower than this case, right? The beam is confined in a narrow region other than this, other than the above two condition. So it looks like the beam is confined in this manner. And here we see this defines the waist of this beam. Okay, the smallest width of this propagation beam, which define the waist. And other type of setup that we have, type of arrangement that we can have for a stable mirror resonator is one concave and one convex mirror resonator. So here we can see this is the concave mirror and this is the convex mirror. And in this mirror, the rays are confined in this manner. And one example is when R1 is minus 80 centimeter, so it's a concave mirror, and R2 is 90 centimeter, which is a convex mirror. And the separation distance between this mirror setup that we have taken is L equal to 70 centimeter. And using this, we calculated what are the values of G1 and G2. So G1 is nothing but 1 plus L by R1, and G2 is 1 plus L by R2. So we calculated the values of G1 and G2, and we first verify whether it is satisfying the stability condition or not. And we see, yes, this setup, this mirror resonator, it satisfies the stability condition. So that means the ray will be confined inside this mirror resonator. And this is one of the visual representation of the confinement. And so these are some, I think, recap of previous section, that is the stability condition. So all of you must have known now what is the stability condition for the mirror, which is G1, G2 should lie between 0 to 1. And these are the stability diagram between G1 and G2. So only the values of G1, G2, which lies in this shaded region. This defines the uh, values of G1, G2 that are allowed and that can form a stable resonator. Other than this value, if you have values here or here or here, these are not allowed. So this will define it. What you say? It's a unstable mirror resonator. Okay. So now, I think this is the same one with different. This is the same one concave and one convex mirror resonator, but a different value of Ym and theta. So here, I think you have seen some narrower beam. So the width is narrow here. Now, for different value of Ym, it may become this much, but the ray will be confined inside this resonator. And for unstable, that is, so instability you can easily verify from the value of G1 and G2. And if you see the ray paths, you can easily see these rays are escaping out from this mirror resonator. So that means the rays, they are not easily confined inside this. They are eventually escaping out from this mirror resonator. Okay, so that means if you these are unstable, so we can't take it to construct a mirror resonator for the laser condition. Okay, so these are this concludes our ray pass in a spherical mirror resonator. So do you have any doubt in this all these parts before moving to our next section? So let us first solve this one, then we'll move into the next section. The first one is draw qualitatively the resonator stability diagram and to mark the position of the following resonator comprising of one is two concave mirrors of radius of curvature 20 centimeter each separated by a distance of 50 centimeter. So let us see the first case. So first case is concave mirror of R1 and R2 at 20 centimeter. So as it is a concave mirror, so that means R1 and R2 is minus 20 centimeters. So please remember the sign convention before solving the problem. Okay, so for concave mirror, R1 and R2 is negative. So it is minus 20 centimeter. And L, it is given, it is 50 centimeter. So that means the value of G1 and G2 that we will get is minus 1.5. And if you want to locate this position, so it lies here. Minus 1.5, right? So it will lie here, not there. So here we can clearly see this point is outside the stability diagram. So that means it is a unstable resonator. And for the second case, we have two convex mirror of ROC 50 centimeter each, separated by a distance of 25 centimeter. So here it is a convex mirror, so that means R1 and R2 is 50 centimeter, right? And L it is given 25 centimeter. So that means we will get the same value of G1 and G2 as you have seen in the previous case, because so G1 and G2 we get is 1.5, 1.5 and 1.5. So that means the position is here. So this is also unstable resonator. In the third case, it is one convex mirror of ROC 80 centimeter and one concave mirror of ROC 80 centimeter separated by a distance of 40 centimeter. So we have one concave and one convex with same radius of curvature. So R1 it's a convex, so it is positive 80 centimeter, and R2 it is negative minus 80 centimeter, and L is given minus 40. So if you calculate it, we have G1 is 1.5 and G2 is 0.5. So the value of G1 is greater than G2. So if you see the position, the G1 it is 1.5. So that means this is around G1 is around here and G1 and G2 is 0.5. So this position. So it this C point it lies inside the stability the shaded region of the stability diagram. So that means this value, that is this mirror setup, one concave and one convex, it can form a stable resonance. And the third is the one plane mirror resonator, one plane mirror and one concave mirror of ROC 60 centimeter separated by a distance 30 centimeter. So one is plane mirror, that means R1 is infinity, and another one is a concave mirror of ROC 60. So that means R2 is minus 60 centimeter and L is 30 centimeter. So that means the G1 and G2. G1 will get 1 and G2 will get 0.5. And if you want to locate this point, so this point will lie here. So this point is also inside the shaded region. So that means this also form a stable resonator. So only the C and D point they are lying inside this shaded region. So they will form a stable resonator if we take this setup to form a mirror resonator. So these are all about the week 6 content that we have seen in the lecture. Now we'll solve, before moving to week 6 content, let us solve some few problems, some additional problems. So please go through the first question once. So let us see what the question 1 says. So question 1 is, for two concave mirror resonators separated by a distance L equal to 1 centimeter, what would be the value of R2 such that rays would be confined inside the resonator when R1 is 2 centimeter? So let us see what is given to us. So L is given, that is the separation between these two mirror, and these are two concave mirror. This one is radius of curvature R1, this is R2. and R1 is given, it is 2 centimeter. Now it is asking what is the value of R2 such that the ray will be confined inside this 2 concave mirror resonator. So that means this has to satisfy the stability condition, which is 0 less than G1, G2 less than equal to 1. And G1, G2 value you can easily calculate from this form. G1 is 1 plus L by R1, and for concave mirror it is 1 minus L by R1. So L is already given, it is 1 and R is 2. So this means this is 0.5. And G2 value, this is 1 minus L by R2, and it is 1 minus 1 divided by R2. So we just have to put in the stability condition to get the value of R2. So 0 less than 0.5, 1 minus 1 by R2 less than equal to 1. So if you take this part, this is 0.5, 1 minus R2 is greater than equal to 0. 0.5 minus 0.5 by R2 is greater than 0. So that means this is, so R2 should be greater than equal to 1 for the mirror to satisfy the stability condition. So for values that are greater than equal to 1 centimeter, we'll have rays confined inside the resonator. Okay, so this is the condition that we have to get. So this is all about this problem. Now let us move to the next one. So before solving it, please go through this question once. So this question has two parts. One is, so let us see what is the question is about. So the question says a plano concave mirror with a concave, so a plano concave mirror. This is the first one. With a concave mirror of radius of curvature r equal to 50. So this means r is minus 50 centimeter and a separation distance d. So that means here d means L for our case. So L is 30 centimeter. So this separation is 30 centimeter. Now it is asking calculate the RT means ray transfer matrix. Calculate the ray transfer matrix for one round trip. So when the ray goes from here to here and comes back to here, what is the ray transfer matrix for one round trip inside this plano concave mirror resonator? So if ray transfer matrix is enough to find out what is the value of A, B, C, D. So you have to remember the how you can get the value of ray transfer matrix. So first one is, so the first component is, so when inside this mirror resonator, so ray will travel from here to here. So we'll have a matrix for that, propagation matrix, which is 1 L 0 1, right? Then the ray from here they will reflect it towards the first mirror. So it will, when this reach here, it will be reflected back. So we'll have a matrix for this reflection from a spherical mirror resonator. So So this is nothing but 1, 0, 2 by r 1. Now after reflection, the ray will move towards this plane mirror. So now we'll again have a ray transfer matrix for propagation, which is 1L01. From after propagation, the ray will again reflected back. So we'll have a reflection for that. For plane mirror, it is 1001, right? So these are the 4 matrices for one round trip. So if you, let's say, for this setup, you started from here. So it propagate to the second mirror, it get reflected, again propagate towards the plane mirror, then it reflected. So this defines the one round trip, right? So this means this is the RTM of the one round trip for this setup. So now you just have to multiply the matrix to get the value of the RTM. So let us put the value. This is 1001. L is 30, 01, 10, 2 by R. So 2 by R is 2 by minus 50. So this is minus 0.04. So minus 0.04, 1, 1 L. L is 30, 1. Now you have to multiply the matrix only. So let me ask whether everybody knows how to multiply a matrix. If not, then I can explain, or I will assume you know how you can multiply one matrix with other matrix. So, okay, let me show one step. So let us take, we are multiplying these two matrices. So we have to first multiply the first row with first column. So this will give 1 into 1 plus 0 into 0. So this will give 1. Then we have to multiply the first row with second column. So that means this will give 1 into 30, 0 into 1. So 30, it will give 30 only. Now this is 2 one element, right? So we have to multiply second row with the first column. So this will give minus 0.4. Now this is 2, 2. So we have to multiply second row with second column. So this will give a value of 1. So minus 0.4 into 50. So this will give minus 1.2. So this, in this manner you can multiply the matrix. So you have to get the element. So if you multiply all these matrix, what you will get? You will get 130 minus 0.04 and minus 0.2. So if you multiply all these matrix, we'll get these values. Okay. So just multiply row with column to get the value of the matrix element. Now we have the RTM, which is this. So this part is over. Now for the second part, it is telling determine the position and the angle of ray after one round trip if the initial position is 1 mm and initial angle is 0.01 radian. So initial position is given and initial angle is given. Now we have to find out what is the position after one round trip. So we have the ray transfer matrix, which is A, B, C, D, which is equal to 130 minus 0.04 minus 0.2. Now, if you want to find out what is the value of final position, that is y and theta, if initial position is y0 and theta 0. So these are related by the ray transfer matrix, which is 130 minus 0.04 and minus 0.2. And y0 is given. Y0 is 1 mm, right? It is given 1 mm. And theta 0, that is the initial angle, it is given 0.01 radian. 0.01 radian. So what do we have now? This one is 0.01. So if you multiply it, so we'll get the value, which is 1.3 mm and minus 0.042 radian. So this will be the position of the ray and the angle that the ray will make with the horizontal after one round trip. Okay, so we initially started with 1 mm and 0.01 radian. Then after one round trip, the ray position it is 1.3 and the angle is minus 0.042 radian. So is this clear to you? Is this problem clear to you? The important point is here is where we have to calculate the ray transfer matrix. This is important. After that, everything is easy. Okay, so if you don't have any doubt, let us move to the final problem. So please go through the question once. So let me read out the question for you. The ray transfer matrix after one round trip for a particular open resonator formed by two mirror is given by ABCD equal to 1P01. So let me write down the ray transfer matrix here. ABCD equal to 1P01, 10Q1, 1P01, 10R1. So this is the ray transfer matrix after one round trip. And it is given P is greater than 0, Q is less than 0, R is greater than 0. So these are given in the question. Now it is asking the resonator is whether the resonator is a convex concave mirror resonator, or it is a confocal mirror resonator, or it is a plano convex mirror resonator, or it is a plano concave mirror resonator. So what is the type of resonator when we have this condition? When we have the RTM, ray transfer matrix, as this form. So to solve this problem, one thing you have to remember is the ray transfer matrix for each ray process. Like what are the ray transfer matrix for propagation, what are the ray transfer matrix for reflection in a plane mirror or in a spherical mirror resonator. So we have seen for propagation, we write down as 1L 01, right? So L is the separation between the mirror resonator. This is for propagation RTM. So please remember all these small things so that you can easily solve the problem. And for a reflection from a spherical mirror, we have 1, 0, 2 by R, 1. This is for reflection from spherical mirror resonator. And what else? And for his reflection for a plane mirror, we have 1, 0, 0, 1. This is reflection RTM for a plane mirror resonator. Okay. It's not clear, I think. So this all you have to remember. Now let us see what does this matrix represent? What does each matrix represent? So the first one is 1, 0, R1. So this typically indicate it's the reflection matrix with a value of 2 by R equal to R, right? This form. So it's a reflection matrix. And here you can see R is greater than 0. So that means this 2 by R, it is also greater than 0. So that means the value of R must be positive. So it's a convex mirror. So it's a reflection from a convex mirror, right? Convex mirror. Now the second matrix, which is 1P01. So it clearly indicates it's a propagation RTM matrix, which is value. So it's a propagation matrix with value 1P01. So that means the P value is nothing but the separation between the two mirror resonator. Okay. So if the question asks what is the other than this, where it may ask what is the separation between these two mirrors, then you can easily see the value of L is here, which is P, and P is greater than 0. Now the third matrix, which is 1, 0, Q1. It is also a reflection matrix from a spherical mirror. Now we have to see what is the sign of this Q. So here it is given Q is less than 0. So that means R is less than 0. So it is a concave mirror. So it is a reflection from a concave mirror. Now this again, it's a propagation matrix. So the space L. So we have two mirror, two propagation and two reflection. One reflection from convex and one reflection from concave. So that means, so if I write down again, so we get ABCD equal to 1P01, 10Q1, 1P01, and 10R1. So this one is reflection RTM from convex mirror. This is a propagation RTM, and this is reflection RTM for concave mirror, and this is again propagation RT. So that means the setup here is a concave and convex setup. So that means the setup is the mirror resonator are convex, one convex and one concave mirror resonator. So this is the way which we can calculate what is the mirror arrangement when you have RTM in this way. Okay, so this is all about the Wix content. So before moving to week 7, let me ask again whether you have any doubt in the problem solved. Okay. Okay, let us move to the week 7 then. Then we'll solve the problems also. So in week 7, we learned about what are the modes, what are the transverse modes of a spherical mirror resonator. So transverse mode, as the name indicate, it is transverse, that is transverse to the propagation. It is perpendicular to the propagation of the ray. So propagation, we are assuming the propagation is happening in the z direction. So that means the transverse plane is xy plane. So transverse mode, it indicates the transverse field distribution. And the transverse mode, these are those modes that are self-reproducing field distribution inside the resonator. So that means the definition for this, the definition for self-reproducing field distribution is this field satisfy this condition. Okay. So F0, let's say we have a initial field distribution. So we have two mirrors here, M1 and M2, which are separated by distance L. Now, when we have a initial field distribution, which is F0, XYZ. Now, after one round trip, let's say the field distribution is F1, XYZ. Now, if the field distribution after one round trip, if it is related to F0 by this equation, then we can tell this is a self-reproducing field distribution, and these are the transverse modes of the resonator. So the transverse mode, which is self-reproducing, this has to satisfy this condition, which is F1. After one round trip, the field distribution will be similar to the initial field distribution with a factor sigma. Okay. So if you see the diagram here, you can see we have taken a Gaussian field distribution. So if you see the red line here, so it's the initial field distribution. Now it propagate during propagation, its field profile, it remains the same. It's Gaussian. Only the width and the amplitude is changing. Now, if you see after one round trip, the field distribution is given by this blue curve. Okay, so this is given by this blue curve. This is F1. This is also, you can see, this is also similar to the field distribution of F0. Only a change in the amplitude and the bandwidth it is occurring. So if it is satisfying this condition, we can tell these are transverse mode of the resonator. And the sigma here, it is a amplitude attenuation factor, which is sigma equal to mod sigma e to power minus I phi. So mod sigma, it's the amplitude attenuation factor, and phi, it indicates the accumulated phase during one round trip. And for transverse mode, this accumulated phase, this is to satisfy this condition, which we have seen earlier also. If you recall the standing mode condition, this a similar condition we have seen in that case also. So for transverse mode, we have to these modes have to satisfy phi must be equal to a integral multiple of 2 pi. And typically the value of mod sigma, it can be when it is 1, then the F1 value is equal to F0, but it is less than 1. That is, some amplitude is decaying because of some propagation loss or scattering loss inside this mirror resonator. So the value of sigma it is less than equal to 1 and defines the amplitude attenuation factor per round trip. Okay. And in this spherical mirror resonator, we have seen the solutions. So if we neglect the diffraction loss, and if you take the paraxial approximation, that is the ray makes small angle with the optical axis. Okay. Under this condition, the analytical solution we have get is, sorry, one is Hermite-Gauss mode and one is Laguerre-Gauss mode. So in first case, we solve the ray propagation solution in the Cartesian coordinate, which is x, y, z. So in that case, we will get Hermite-Gauss solution. And if the mirror resonator, if we are taking the satisfy cylindrical symmetry, then in that case, we can solve this problem in the cylindrical coordinate, which is r theta phi or r phi z. So in that case, we'll have Laguerre-Gauss modes. So we'll see Hermite-Gauss in this course. So let us see how we can get the transverse mode. So to get the value of F1, we typically take the Fourier optics approach. Okay. So in Fourier optics approach, what we have, we initially start with the initial field distribution, which is F0, X, Y, Z0. So we have a field distribution at value Z0. Now when the field propagate, to get the value of, so it will propagate to the second mirror, right? So when the field reach here, what is the field distribution? How you can calculate it? So we take Kirchhoff integral to calculate what is the value of field in the second mirror when it started with F0, XY, Z0. So this field, it is given by G, X dash, Y dash, Z0 plus L. And this is given by the integration of the initial field distribution with a point source term, and the integration is over the surface dx and dy. So we started with this initial field distribution and we take the Kirchhoff integral to find out what is the value of this field in the second mirror, which is G x prime y prime z0 L. And now in the second mirror, the value of field is G. Now what will happen? The field will get reflected back. So for this case, we'll add, for reflection, we'll add a factor mu2 in the field G. So this mu2 is due to the reflection from the mirror. So mu2 we typically write it as mod mu2 e to power minus I chi. So chi is nothing but a phase factor because of the reflection from the mirror, and we can typically write it as k by r x prime square plus y prime square. Okay. And now let us see what we have. So initially started with f0 xy z0 initial field distribution. This field will propagate through the space between these two mirrors. Now when the field reaches the mirror surface M2, the field distribution can be given by G x prime y prime z0 plus L, which we got from Kirchhoff integral. Now from this mirror, it will get reflected, and a factor mu2 will be added due to the reflection from the second mirror. And this U2G, this will again propagate to the first mirror. For that, we'll have a, so when it reaches the first mirror, we'll again have a field distribution H. We can get it from the Kirchhoff integral again. Now again at the first mirror, it will be reflected back towards the second mirror. So we'll have a value mu1 h. So this is first round trip. So after first round trip, we'll get the value of field distribution, which is f1 xy z0. And if, as you have seen, if this f1, it is some multiple of some sigma times f0 xyz0, where sigma is this, then we can say this is a transverse mode of the resonator. And again, for the field to be a transverse, the phi should satisfy this condition, which is phi should be integral multiple of 2 pi. Okay, so you have to remember this condition, which is phi is integral multiple of 2 pi. So the effect of this reflection by spherical mirror, we have seen, we add a factor of mu in the final expression, which is mod of mu1, mod of mu e to power minus I into the phase factor phi, which is k by r x prime square plus y prime square. And mu is the amplitude attenuation factor, which is related to the reflectivity of mirror. So reflectivity is nothing but mod mu square. Okay. And this we have already seen before. This is for concave mirror, we have r less than 0, and for convex mirror, it is greater than 0. Now let us see what are the expression for transverse mode. So we have seen, so please refer to the books if you want a derivation of this mode. Otherwise, we'll see the final expression only. So the final expression is this transverse mode. So these are Hermite-Gauss modes. So we'll have a Hermite polynomial, which is these terms, HL and HM. These are Hermite polynomial, and there is a Gaussian function here. Okay. And these are the phase factor. One is the phase factor, which may be due to the reflection from the mirror, and other is the amplitude of this Gaussian function, Hermite-Gauss mode. So these are some parameters that we have to remember, like the Rayleigh range. So Rayleigh range Z0 equal to pi W0 square by lambda. This defines the Rayleigh range. And zeta of Z is nothing but, so zeta of Z is here. Let me take a different color. So this is zeta of Z. So zeta of Z is given by tan inverse Z by Z0. And WZ that we have seen in the question, in the equation, it is defined the spot size. It is related to W0, 1 plus Z by Z square root over. And W0 defines the waist of this beam. Okay, we'll see later what is this waist size. And RZ is the radius of curvature of this wavefront. Okay. So similar to the waist size, we have spot size relation, that is radius of curvature relation, which is RZ equal to Z times 1 plus Z0 by Z square. So this defines the ROC of the wavefront at any Z inside this plane mirror resonator. Okay. And HL and HM, these are already Hermite polynomial. Now we'll see how the beam is affecting inside this two concave mirror. So let us take two concave mirror, which have ROC. First one is R1 and second one is R2, and these are separated by a distance L. And we started with so if you see the Gaussian mode, it is confined inside this mirror resonator, and at each Z value, let's say it is Z1, Z2, this is Z0, Z3, Z4. It at each point the profile is same, but only the amplitude and the uh, width of this beam is changing. So that means the way the spot size, which is W0, and the ROC, they are changing at different location inside this plane mirror resonator, inside this resonator. Okay. So ROC, this is the radius of curvature of the beam. So I think these are all small parameters and some small information that you need to know. That is, what is the relation between the spot size and the waist ROC with Z. So let us see now the intensity distribution. So before that, let us see what is the Hermite polynomial. So these are some Hermite polynomial for H0, like so we have Hermite polynomial HL here and HM here. So when L equal to 0 or when M equal to 0, the Hermite polynomial is H0x, which is 1. And for when L equal to 1 or when M equal to 1, we have Hermite polynomial is H1x, which is 2 times of x. And when L equal to 2 and M equal to 2, we have Hermite polynomial is 4x square minus 2. And if we know any two values of Hermite polynomial, that is the previous two values of Hermite polynomial, then we can easily calculate what is the next Hermite polynomial expression using this recurrence relation. Okay. So these are all you don't have to remember. At least I think H0 and H1, this you need to know. And otherwise, if any higher order or Hermite polynomial is needed, it will be mentioned in the question. Now let us see what is the intensity distribution. So intensity, it is given by mod of ULM square. So if you take the square of ULM, so we will get expression like this. Okay. Now in the next step, what we have done, so we have make a substitution. That is, we have taken zeta as root 2x by wz and eta as root 2y wz. And using this substitution, we have defined two new function, which is GL zeta, which is related to the Hermite polynomial as HL zeta e to the power minus zeta square by 2. And we have another new function, which is GM eta, which is related to the next Hermite polynomial HM eta e to the power minus zeta square by 2. From that, we get the intensity expression as this equation. From this, let us see what is the lowest order mode of this resonator. So for the lowest order, we'll have the value of L is 0 and the value of M will be 0. So for that case, what we have? So the intensity, it is given by this expression. This is the final expression after putting L equal to 0 and M equal to 0. Here you can see there is a Gaussian function here, right? E to 1 minus x square plus y square into 2 divided by w square z. And there is some amplitude factor here. I0 w by wz, w0 by w square. And if you plot this intensity distribution, this is given in this figure. So, so it's a Gaussian term. It were minus 2x square plus minus 2y square divided by w square. So that means in the x direction, it's a Gaussian function. Also in y direction, we'll have a Gaussian function. Similar to the, now again in the negative x, we'll have a Gaussian function. So let me draw another place so that it is clear to you. So what I mean to say, so we have a pattern in this space. So in the x direction, it is Gaussian. In the negative x, it is also Gaussian. Now in the y direction, it is Gaussian. In the negative y, it is also Gaussian. So that means you got a circular intensity pattern here, right? Which decreases monotonically as we increase the value of x and y. So if you see this figure, this shows the fundamental mode, that is TEM00 mode of the resonator. So this is a circular pattern. So which have decaying intensity as we move from the center of this intensity pattern. So that means the lower order mode is a Gaussian mode. And this is interesting because the Gaussian mode, if you see the intensities, the energy, it is highly confined in the center. So that means the energy of the ray will be confined in the center. We'll see some of the advantages of using the Gaussian mode. Now let us see what is the intensity distribution for the next higher order mode. That is when either L equal to 1, M equal to 0, or L equal to 0, M equal to 1. So for this, we'll have I10. So let us see I10, that is when L equal to 1, M equal to 0. So intensity is given by this expression. Now if you see G1 zeta, it is related to the Hermite polynomial H1 zeta. And if you see the Hermite polynomial, H1 zeta is nothing equal to 2 zeta, right? S0 zeta is always 1, the lowest one. But the H1 zeta is 2 zeta. Now when you take the square, it is 4 zeta square. So this is plotted in this red curve. You see this figure? So this red curve is 4 zeta square. And second function is G0 eta, which is related to S0 eta. So S0 eta is 1. So that means the field distribution will be again a Gaussian field distribution, which is shown by this dotted line. So if you see here, it is a dotted line. Now the resultant field will be, so in the center, so if you see, in the center it will be 0. Here it will be 0 because 4 zeta square is 0. So we'll see a 0 in the center. And as we move away from the center, which field will dominate? This 4 zeta square will dominate because this is decaying monotonically, right? Only the dominating factor is 4 zeta square. So that means the field will again increase. Now it will again decrease the both side because after some time it will be eventually 0. The Gaussian field distribution, it will be 0. So we'll see the pattern of the next higher mode is this pattern. Now if you see at the screen, we'll see two circular or two Gaussian field distribution on either side of this center. Okay. So for TEM00, we see the field distribution as this. Now for the next higher order mode, which is TEM10, the field pattern is this much. And for the next higher mode, you can easily calculate. So these are some field profile that has been taken from Wikimedia. So as you have seen, the 00 mode is this, where we have seen a circular pattern here. 10 mode is where we see a null point, that is a 0 point in between this circular spot. And 20, we see two 0 point along this x direction. So if you take this is x and this is y. So we see for 2, 0, there are 2 0 points or 2 null points along this direction. 3, 0, we see 3 0 points. Again, if you now take instead of 1, 0, if you take 0, 1, so we see there is 1, 0 when you move along y direction. 1, 1 means we'll see a 1, 0 along the x direction as well as 1, 0 along the y direction. 2, 1, if you guess, we'll get a 2 0 points when we move along x direction and 1 0 point along y direction. And similarly for 3 1, we'll get 3 zeros along x and 1 0 along y. Similarly for 0 2, we'll see we don't see any 0 along the x direction, but we'll see 2 zeros when we move along the y direction. And 1 2, 1 2 is for the case where we'll see 1 0 along x direction and 2 zeros along the y direction. 2 2, 2 zeros along x direction and 2 zeros along y direction. 3 3 is 3 zeros along x direction and 3 zeros along y direction. So let us say we'll have, let's say we have m. So instead of m, let us take I p q. So that means L is p, m is q. So this means we'll give p zeros along x direction and q zeros along y direction. Okay. So in this way, you can find out how many null point or how many zeros you can get for a particular field profile. Okay. So this is one example that has been taken for when P is 1 and Q is 7. If you write I as PQ, so here for I1 7, P is 1 and Q is 7. So if you see in the diagram, when you move along x direction, it's 1 0. And when we move along y direction, it is 7 0. Similarly for I2 6. Okay. I think this is clear to you. Now we'll see what are the resonance frequency of this spherical mirror resonator. So these are already we have seen before. These are Hormite-Gauss mode for the spherical mirror resonator, and there is item here. This is the phase. Okay. And to find out what is the resonance frequency, what you have to do, we have to see, we have to take those values of frequency for which phi, the value of phi is integral multiple of 2 pi, some integral multiple of 2 pi. So that means, let us see what is the round trip. This is phi is the round trip phase. So the for resonance frequency, the round trip phase must be equal to integral multiple of 2 pi. So let us see after one round trip, let us take the round trip expression first. So that means, so one round trip means the ray will start from here, then it will be again reflected back here, then it will start from this position. This is one round trip. So let us take the initial phase here is phi 0 0 z1, and the phase here is phi 0 0 z2. Right? So the phase round trip phase, now you have to, if you want to write down, so this will be 2 times of 0 0 z2 minus phi 0 0 z1. Okay. And phi expression, I think this is, you have to take the expression from here, this expression, and put the value of x and y as 0 and z is Z1 or Z2. If you put it, you will get this expression. And this phase, this round trip phase, it must be equal to some integral multiple of 2 pi for the resonance frequency. So this means this should be equal to 2q pi, where and delta zeta is this term. Now what you have to do, you just have to put the value of k. K is nothing but some k0 in free space wave vector into the refractive index, and free space wave vector is omega divided by c, right? Omega by c, and, and omega is nothing but 2 pi frequency, 2 pi mu, 2 pi mu 0 divided by c. And so we just put the value of k here and rearrange this expression to get the value of the frequency. So the frequency we got is nu q is this expression, and if you see the final form, this for spherical mirror resonator. For spherical mirror resonator, we have the resonance frequency is nu q is q times of nu f plus delta zeta by pi plus into L plus m plus 1 nu f. So nu f is nothing but the free spectral range that we have seen in the plane mirror resonator. Okay. And if you want to find out what is the free spectral range for the spherical mirror resonator, what you have to do? So nu q is already given. It is q nu f plus delta zeta by pi L plus m plus 1 nu f. And delta, sorry, nu q plus 1, it will be q plus 1 nu f plus delta zeta by pi L plus m plus 1 nu f. So if you take the difference of this two frequency, what you got? Nu q minus nu q plus 1 is nothing but nu f. So nu f is same as the plane mirror resonator. For spherical mirror, we have nu f c by 2nl, and for plane mirror, we have nu f is c by 2nl, and for mirror also we have seen the nu f remains same. Only there is the frequency in the resonance frequency, we see additional factor here, additional term here, which depends on the curvature of this two spherical mirror. Okay, so this is the curvature dependent frequency correction term. And for plane mirror, this delta zeta, it vanishes, so that nu q will do q times of mu f that we have seen earlier. And for a spherical mirror resonator, this delta zeta, it lies between 0 to pi. It depends on the position of the mirror, Z1 and Z2 with respect to Z0. Okay. So for spherical mirror, there is a correction term here. Now, if you see what are the location of this Hermite-Gauss mode. So in addition to the initial position nu q plus 1, we have seen some small some frequency that are closer to nu q because of this correction term of the curvature dependent frequency correction term. So we see the first line will be for L equal to 0, M equal to 0. Next line will be for L equal to 0, M equal to 1, or L equal to 1, M equal to 0. The next line will be L equal to 1, M equal to 1, and other terms. Okay. So in plane mirror, we have only these frequencies nu q plus 1, nu q plus 2, nu q plus 3. But in spherical mirror, in addition to this nu q terms, we have some other frequency lines that are closer to the initial resonance frequency position. And this lines is due to this curvature dependent term. Okay, so these are all about the resonance frequency and the Hermite-Gauss of the mode. Now we'll see the what is the properties of the Gaussian modes. That is the fundamental mode of the spherical mirror resonator. Okay, so for fundamental mode, that is the Gaussian mode, we have seen the intensity distribution, which is I00. So please remember for the lowest order mode, that is the Gaussian mode, both L and M are 0. And we have a Gaussian field distribution in the intensity term. Okay. And for spherical mirror resonator, we see if you see the if you first take the amplitude term U00. So there is an amplitude term here A00 W0 by WZ, and there is a Gaussian envelope which is e to power minus x square plus y square divided by w squared z, and there is a phase term here. Okay, and these are some parameters related to this Gaussian field. So how we define a Gaussian field, right? So we define the spot size of this Gaussian field as Wz equal to W0 1 plus z by z square whole root of, and for any field distribution we have a radius of curvature, which is the radius of curvature of the phase front, which is moving along the mirror inside the mirror resonator. So we have RZ, which is ROC of this phase front is Z times 1 plus Z0 by Z square. And this Z0 defines the Rayleigh range, and this is the zeta terms here. Okay. And if you see the ray paths, we have a Gaussian field distribution here. And as the ray propagate inside this mirror resonator, both the radius of curvature as well as the wave size, the spot size, this changes as the ray, the Gaussian field, propagate inside this mirror resonator. And there will be a position where the wave size will be, the spot size will be minimum. And this position where the spot size is minimum, we define this position as Z0. Okay. So let's say at Z equal to Z0, the spot size is minimum. And for this case, where the spot size is minimum, we define the waist as WZ equal to W0. Okay. So this is the position where the spot size is minimum. And okay, so let us discuss all this in our next slide section. So before ending the section, let me ask whether you have any doubts or any problems or any conceptual doubt in any part of this slide. So we'll see all this in our next section. Okay, if you don't have any doubt, then let us quickly see. No, better to discuss all this in the next section only. So there are reflection, then ROC, what are the effects of reflection on the radius of curvature, and what is remaining? What are the design problem? So reflection, if you can easily see, these are, as you have seen, when the ray get reflected, then we'll see a mu factor here. mu factor in the initial field distribution. So if you have a field here, let's say initial field is f of xyz, then after reflection, there will be a mu factor here. And the chi here is the phase of the field. That is k by rm x square plus y square. Okay. Rm is the ROC, mu is the amplitude attenuation factor. And if you want to find out the reflectivity of the mirror, it is nothing but mu square. Okay. And for transmittivity, you can easily get it from the reflectivity, which is 1 minus mu square. Now, we'll see what are the effects of R on the wavefront of this mirror in the next slide section. Please provide lecture slides for solving problems of the science. So, which lecture slides you want? Week 7 lecture slide, I think you want for this week 7 assignment. Up to week 4, every slides is there. Week 5, 6, and 7. Okay. So, in the NPTEL site, it will take some time to upload this lecture slide. So what I can do, I can upload this the lecture slide that I have in the Google Drive link. There you can get the lecture slide. So one thing I want to make sure you have the link for my Google Drive folder, right? So do anyone, everyone is the link for my Google Drive link. So if you have that link, then please visit that folder. I will upload. Week 6 is already uploaded. If you see in that folder, and I will upload week 5 and week 7 if you want. So you don't take that link. So let me paste it here then, the link of my Google Drive. Okay. This is the link. And I think this link is also shared with all of you. The YouTube video link as well as the drive link is shared. It's there in the NPTEL site also. If you go to the problem solving section, in the tab, in the left side, there is a tab for the problem solving section. If you click on this problem solving section, then you will get a spreadsheet, Excel sheet. So in that, the links, all the links and the YouTube link, it's already there. So is it okay? The link, any other doubts? Okay. Okay. Then let us end the section for today's section. So thank you for joining the section. I think all the slides and all the problems are clear to you. And if not, please feel free to ask me in the next live section. We'll meet on the next Saturday, same time, from 4 to 6, to discuss the concept and to discuss your doubts and solve some few problems. So let us end the section for today. Let us meet on the next Saturday. So goodbye, everyone.